Please subscribe to support the channel. Far out in the depths of the cosmos, there exists a star unlike almost anything else we've ever encountered. A star that beats with a rhythm so precise that it rivals the accuracy of our finest atomic clocks, yet at the same time, it behaves in ways that completely defy our expectations. This star spins faster than the blades of a helicopter, it flares with bursts of radiation that can be detected across light years, and it glitches, as if the very machinery of the universe suddenly stutters, revealing a hidden mechanism we cannot yet fully comprehend. This is the Vela Pulsar, one of the most mysterious and captivating stars in the entire universe, a celestial beacon that has fascinated astronomers for decades and continues to baffle them with secrets that no telescope has yet unraveled. The sheer scale of its mystery is astonishing. It is not merely another point of light in the night sky. To those who study it, the Vela Pulsar is a cosmic puzzle box, packed with riddles about time, matter, energy, and even the very fabric of space itself. It radiates with the ghostly echo of a long-dead star, yet it is alive with motion and energy that could tear apart our very sense of physics if we dared to stand too close. Every rotation, every pulse, every strange anomaly it emits is a signal from the depths of space, a message written in the language of the universe itself. And through those signals, we begin to see the edges of a world where matter behaves in ways we cannot replicate on Earth, where gravity crushes atoms into unfamiliar forms, and where time itself bends under pressures so immense that Einstein's theories are not just tested, they are stretched to their limits. When we talk about stars, we often think of their beauty, their light, or their role in the tapestry of the heavens. But when we talk about the Vela Pulsar, we are talking about something fundamentally different. We are talking about a star that exists at the very edge of possibility. A star that has survived its own death, transformed into a relic of cosmic violence, yet continues to spin and blaze with an energy that dwarfs anything humanity has ever created. It is a lighthouse in the night of the cosmos, but also a ticking clock, a laboratory of physics, and above all, a mystery. The Vela Pulsar is not just another object catalogued in astronomy, it is a phenomenon, a challenge, and perhaps even a hint at truths the universe has yet to reveal to us. This is why, when astronomers look at the Vela Pulsar, they are not just studying a star. They are staring into a keyhole that might unlock the secrets of neutron stars, supernovae, and the fate of matter itself. The Vela Pulsar is more than just a star, it is one of the universe's strangest storytellers, and every rotation of its core carries with it a tale older than human civilization. And so, as we set out on this journey to understand the Vela Pulsar, remember this: it is not just about what we know. It is about how much we still do not know, how much lies hidden, waiting to be uncovered. The mystery of the Vela Pulsar is a reminder that even after centuries of studying the heavens, the universe still holds its greatest secrets close. To truly grasp the awe-inspiring nature of the Vela Pulsar, we first need to understand the larger family it belongs to, the pulsars themselves. The word pulsar comes from pulsating star, though that name is a little misleading. A pulsar is not a star in the traditional sense, glowing brightly like the sun, but rather the collapsed, ultra-dense core of a once massive star that exploded in a supernova. When such a star ends its life, the outer layers are blown away in one of the most powerful blasts in the cosmos, but the core doesn't vanish. Instead, it undergoes a catastrophic transformation, squeezing matter into one of the strangest forms of existence we know, a neutron star. A neutron star is like nothing we can compare to on Earth. Imagine taking the mass of the Sun, which is about 330,000 times the mass of Earth, and crushing it down until it fits inside a sphere only about 20 kilometers across. That's smaller than the size of many cities. The density of such an object is so staggering that a single teaspoon of neutron star material would weigh billions of tons, more than the entire mass of a mountain. Gravity has forced protons and electrons to fuse together into neutrons, leaving behind a core of almost pure neutron matter. It is nature's most extreme pressure cooker, creating a state of matter we cannot replicate in any laboratory. Now, not every neutron star is a pulsar. What makes a neutron star into a pulsar is its magnetic field and its rotation. When the star collapses, it spins faster, just like a figure skater pulling in their arms to spin quicker. Its magnetic field, already powerful, gets concentrated to absurd levels, billions of times stronger than anything we can generate on Earth. This intense magnetic field channels beams of electromagnetic radiation, radio waves, visible light, X-rays, even gamma rays, outward from the star's magnetic poles. But here's the catch: the star's rotation axis and its magnetic axis are usually not aligned. This means the beams don't shine in all directions evenly. Instead, as the star spins, these beams sweep across the sky like the rotating beam of a lighthouse. From Earth, if one of those beams happens to cross our line of sight, we see a regular pulse of radiation. That pulse can be as frequent as hundreds of times per second, depending on how fast the neutron star is spinning. To us, it looks like the star itself is flickering rhythmically, but in truth, we're simply catching the flash of its beam every time it points our way. This is why pulsars are often compared to cosmic lighthouses. They are dark most of the time from our perspective, but when their beam sweeps across our world, we detect their signal with astonishing regularity. This discovery was revolutionary. When pulsars were first detected in the late 1960s by Jocelyn Bell Burnell and Anthony Hewish, the signals were so unnervingly precise that some astronomers wondered if they could be artificial. They were nicknamed LGM, short for Little Green Men, because the pulses arrived with the accuracy of a perfectly engineered signal, as if some distant intelligence were sending a message. Of course, we now know they are natural, but the fact that a collapsed star can keep time better than our most advanced clocks is still mind-bending. The pulsar phenomenon also teaches us something profound about physics. These beams of radiation are powered by the star's rotational energy. As the pulsar spins, it gradually slows down, and the energy lost in that braking process is released in the form of electromagnetic radiation and charged particles. This means that a pulsar is like a giant, decaying flywheel of the universe. Its spin is energy, and its beams are the way it spends that energy across millennia. Some pulsars spin hundreds of times per second, called millisecond pulsars, while others are slower, with only a few rotations each second. Yet in every case, the precision of their pulses has made them invaluable tools for astronomers, who use them to probe the deepest questions of astrophysics. And so, when we talk about a pulsar, we are not just talking about a dead star. We are talking about a star reborn in a new form, transformed into an engine of cosmic rhythm, one that shines not with steady light but with flashes that tell the story of its incredible journey from life, to death, to an afterlife as one of the most exotic objects in the known universe. It is within this remarkable family of objects that the Vela Pulsar belongs. And yet, even among pulsars, each one mysterious in its own right, Vela stands apart. It is faster, brighter, and stranger than most, and it holds within its ticking pulse secrets that even the most advanced physics has not been able to unravel. To understand why, we must look at how these cosmic lighthouses are born in the first place. For the story of any pulsar, including Vela, begins in the fiery death throes of a star. The story of a pulsar's birth is one of the most dramatic and violent processes in the entire cosmos. A process that turns a shining giant of a star into something so compact and strange that it stretches the very limits of our imagination. To understand how pulsars are formed, we must step back and look at the life cycle of massive stars, because pulsars are not ordinary remnants, they are the aftershocks of stellar death on a colossal scale. Stars, as massive balls of gas, live their lives in a delicate balancing act. Gravity, the great inward pulling force of the universe, constantly tries to crush the star inward. Opposing this is the outward pressure created by nuclear fusion, the process by which stars burn hydrogen into helium, and later, heavier elements. For millions to billions of years, this tug-of-war keeps the star stable. In small stars like our Sun, the process ends relatively gently, with the outer layers puffing away into a beautiful planetary nebula and leaving behind a white dwarf. But for massive stars, those at least 8 times more massive than the Sun, the ending is not gentle at all. As these giants reach the later stages of their lives, their cores begin fusing heavier and heavier elements. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, and so on, building up layers like an onion. Each layer burns at higher and higher temperatures as the star fights against gravitational collapse. But this process has a limit. Once the core of the star begins to fuse iron, it reaches a dead end. Unlike lighter elements, iron cannot be fused into heavier elements while releasing energy. Instead, fusing iron consumes energy. This spells disaster for the star. Without the outward pressure of fusion to counteract gravity, the core collapses in on itself in less than a second. Imagine the mass of our Sun being crushed into a space only a few kilometers across almost instantaneously. That is the scale of this collapse. The outer layers, unable to stop their plunge, slam into the collapsing core and rebound outward in a titanic explosion, a supernova. For a brief time, the star outshines entire galaxies, releasing more energy in a few seconds than our Sun will release in its entire lifetime. Ancient civilizations may have seen such explosions flare in the sky, mistaking them for new stars being born, not realizing they were watching the death throes of giants. What remains after the chaos depends on the original star's mass. If the star was extremely massive, perhaps 20 or more times the mass of the Sun, the collapse may go so far that not even neutrons can resist gravity, and a black hole is formed. But if the star is slightly less massive, the collapse halts at a different point. The core becomes so dense that protons and electrons are squeezed together to form neutrons, creating what we call a neutron star. This is the birthplace of a pulsar. In this newborn neutron star, the physics is unlike anything else in the known universe. The density is so extreme that a sugar cube of neutron star matter would outweigh Mount Everest. The magnetic fields, amplified by the collapse, are trillions of times stronger than Earth's. And because of the conservation of angular momentum, the same principle that makes an ice skater spin faster when pulling in their arms, the collapsing star spins at incredible speeds. A star that once took days or even weeks to complete a rotation now spins many times each second. This rapid rotation, combined with the magnetic fields, produces the iconic beams of radiation that define a pulsar. The birth of a pulsar is not the quiet fading away of a star, but the spectacular aftermath of a cosmic detonation. It is both an ending and a beginning, the end of a star's life as we knew it, and the beginning of a new life as a cosmic lighthouse, sending signals across the universe. These objects are like scars written into the sky, marking the locations of ancient supernovae and preserving the memory of those explosions in the form of precise, rhythmic pulses. And so, each time we detect the signal from a pulsar, we are not just listening to a star. We are hearing the echo of a supernova, the whisper of a collapse so intense that it defies human imagination. This is the origin story of all pulsars, and it sets the stage for understanding why the Vela Pulsar is such a remarkable member of this family. Because while all pulsars are born from death, not all are created equal. Some spin faster, some shine brighter, some glitch unpredictably, and Vela, among them, has proven itself to be one of the most fascinating and mysterious of all. As we turn our gaze from the general birth of pulsars to the Vela Pulsar in particular, we step closer to one of the best-studied and most puzzling neutron stars in the galaxy. Its story begins in the constellation Vela, 1,000 light-years away, where an ancient explosion left behind both a neutron star and a spectacular cloud of cosmic debris. The birth of pulsars is fascinating enough on its own, but when we step into the specific case of the Vela Pulsar, we enter a story that feels almost mythical. The Vela Pulsar is not just another member of the pulsar family. It is one of the brightest, most well-studied, and strangest pulsars known to science. Located in the southern sky, nestled within the constellation Vela, this remarkable object sits at a distance of about 1,000 light-years from Earth. In cosmic terms, that's right in our galactic neighborhood. For comparison, the Milky Way is around 100,000 light-years across, so the Vela Pulsar is a close neighbor relative to the vast distances astronomers usually work with. That proximity is one of the reasons Vela has become such an important subject of study. It's close enough for us to observe in extraordinary detail, giving us a rare front-row seat to one of nature's most mysterious experiments. The constellation Vela, whose name comes from the Latin word for sails, is part of an ancient, much larger constellation called Argo Navis, which represented the legendary ship Argo from Greek mythology. Argo Navis was eventually divided into three smaller constellations: Carina, the keel, Puppis, the stern, and Vela, the sails. It is within these celestial sails that the Vela Pulsar resides, shining not in visible light like the stars around it but as a beacon of pulsing radiation across multiple wavelengths: radio, X-ray, and even gamma rays. For astronomers, Vela is not just another point of light but a multidimensional laboratory of physics. What makes the Vela Pulsar stand out among the thousands of pulsars that have been catalogued? First, its brightness. In the radio spectrum, Vela is exceptionally strong, making it one of the easiest pulsars to detect with ground-based telescopes. But even more impressively, in the high-energy regime of gamma rays, it is among the brightest sources in the entire sky. This is no small feat. Gamma rays are the most energetic form of light, and to shine as brightly in gamma rays as entire distant galaxies is a sign of just how powerful this neutron star really is. The Vela Pulsar pumps out energy on a staggering scale, and because it is so close, its emissions reach us with far greater clarity than most other pulsars. Second, its speed sets it apart. The Vela Pulsar rotates about 11 times per second. While this isn't the fastest pulsar we know of, some millisecond pulsars spin hundreds of times per second. It is still breathtakingly fast when compared to everyday scales. The Earth rotates once every 24 hours. Vela, a sphere only about 20 kilometers wide, spins 11 times every second. That's like compressing the mass of the Sun into a city-sized ball and watching it spin faster than a helicopter blade. The energy contained in such a motion is immense, and it radiates outward in the form of precisely timed pulses that reach us like the steady ticking of a clock. But perhaps the most intriguing reason the Vela Pulsar stands out is its personality, if we can call it that. Unlike many pulsars that tick along with monotonous regularity, Vela is known to glitch. These glitches are sudden, unpredictable jumps in its rotation rate, as though the star hiccups or momentarily speeds up. Such events are not only rare in pulsars but also immensely valuable, because they give us a glimpse into the mysterious physics happening deep within the star, physics that cannot be reproduced anywhere else in the universe that we can reach. The Vela Pulsar glitches more frequently and dramatically than most other pulsars, which has made it a prime candidate for studying this enigmatic behavior. Another reason Vela is so important is its association with the Vela supernova remnant. Around 11,000 to 12,000 years ago, a massive star in this region of the sky exploded in a supernova. Ancient humans walking the Earth may well have witnessed the brilliant flash in the night sky. What remains today is not only the Vela Pulsar but also the sprawling cloud of gas and dust that was blown outward by the explosion. This remnant stretches across a large portion of the sky and is one of the most studied supernova remnants ever observed. Together, the pulsar and its surrounding nebula form a cosmic crime scene, evidence of one of the most violent deaths in stellar history, preserved in exquisite detail for us to study. Vela's uniqueness also lies in its accessibility across different wavelengths of observation. It pulses strongly in radio waves, providing precise timing data to astronomers. In X-rays, space telescopes have revealed the structure of its surrounding nebula, showing arcs, jets, and shock waves that look almost artistic in their complexity. In gamma rays, satellites like NASA's Fermi Gamma Ray Space Telescope have confirmed that Vela is one of the brightest sources in the entire sky. Each wavelength tells a different piece of the story, like peeling back layers of a mystery. Few pulsars can boast such a complete profile. For scientists, the Vela Pulsar is both a challenge and an opportunity. Its proximity allows for detailed observation, its brightness makes it easier to study, and its peculiar behaviors, like glitches, provide data that no other star can. When researchers want to test theories about neutron star interiors, about how superfluids might behave at nuclear densities, or about how magnetic fields evolve under such extreme conditions, Vela is often their go-to target. It is the pulsar equivalent of a model organism in biology, like a fruit fly or a lab mouse, but on a cosmic scale. And beyond its scientific importance, there's also something profoundly poetic about Vela. This tiny, dense object, no bigger than a city, is the surviving heart of a once massive star that ended its life in a spectacular supernova. Now, thousands of years later, it continues to spin and pulse, its light reaching us across the gulf of space. It is, in a sense, a cosmic heartbeat, steady, powerful, and enigmatic. The Vela Pulsar's fame is well earned. It's not only a marvel of astrophysics but also a reminder of how much remains hidden in the universe. For all we know about it, there are still countless mysteries surrounding its behavior, especially those strange glitches that set it apart. But before diving into its peculiarities, it's worth revisiting its origin story in more detail, the supernova explosion that created it. That event, which happened thousands of years ago, lit up the sky and left behind some of the most breathtaking cosmic debris ever recorded. The Vela Pulsar's existence is inseparably tied to one of the greatest explosions nature can produce, a supernova. Roughly 11,000 to 12,000 years ago, long before human beings built cities or even discovered writing, a massive star in the region we now call the constellation Vela reached the end of its life. It had burned through its fuel, forged heavy elements in its core, and finally reached the inevitable point of collapse. What followed was a detonation so powerful that it reshaped the surrounding interstellar medium, created a pulsar, and left behind a remnant that astronomers are still studying today. This event was the birth of the Vela Pulsar. To understand the enormity of what happened, imagine a star at least 8 to 20 times the mass of our Sun. For millions of years, it shone brilliantly, fusing lighter elements into heavier ones deep in its core. But once the fusion of iron began, the star was doomed. No further energy could be generated to counterbalance the crushing force of gravity. Within seconds, its core collapsed, and the outer layers came crashing inward at speeds reaching a significant fraction of the speed of light. The result was an explosion so luminous that, had it occurred in today's skies, it would outshine everything else except the moon. For ancient humans, hunter-gatherers, shamans, and early tribes scattered across Earth, this event may very well have been visible. Imagine a bright star suddenly flaring into the night sky, a beacon that remained for weeks or months, dominating their view of the heavens. They had no telescopes or astrophysics to explain it, but they would have seen something extraordinary. Some researchers suggest that ancient rock art and oral traditions might contain echoes of such cosmic spectacles, though no direct evidence ties prehistoric accounts specifically to the Vela supernova. Still, the thought that our ancestors once gazed in or at the birth of the Vela Pulsar connects us to this event in a deeply human way. The aftermath of that supernova is still visible today as the Vela supernova remnant, an enormous shell of expanding gas and dust, tangled with shock waves and filaments glowing in multiple wavelengths of light. This remnant spans over 100 light-years across and appears to cover a large portion of the sky when observed with radio and X-ray telescopes. Its tendrils of gas are rich with heavy elements like oxygen, silicon, and iron, the raw materials that will one day be recycled into new stars, planets, and perhaps even life. In this way, the death of the Vela progenitor star was also an act of creation, seeding the cosmos with the building blocks of future worlds. At the center of this cosmic debris field lies the compact remnant, the Vela Pulsar. During the collapse, the star's core was squeezed into a neutron star about 20 kilometers in diameter, with a mass greater than that of our Sun. The conservation of angular momentum meant that as the star shrank, it spun faster and faster, ultimately reaching a rotation rate of 11 times per second. The intense magnetic fields amplified by the collapse became the channels through which beams of radiation would shoot out into space. What had once been the beating heart of a giant star was reborn as a cosmic lighthouse, its rhythm detectable across thousands of light-years. The supernova that birthed Vela was also a source of extreme cosmic energy. The blast released neutrinos, ghostly particles that rarely interact with matter, in quantities so vast that for a brief moment, they carried away the majority of the energy of the explosion. These neutrinos streamed through the universe, passing effortlessly through everything in their path, including the Earth. If humanity had detail, the supernova explosion that created it. That event, which happened thousands of years ago, lit up the sky and left behind some of the most breathtaking cosmic debris ever recorded. The Vela Pulsar's existence is inseparably tied to one of the greatest explosions nature can produce, a supernova. Roughly 11,000 to 12,000 years ago, long before human beings built cities or even discovered writing, a massive star in the region we now call the constellation Vela reached the end of its life. It had burned through its fuel, forged heavy elements in its core, and finally reached the inevitable point of collapse. What followed was a detonation so powerful that it reshaped the surrounding interstellar medium, created a pulsar, and left behind a remnant that astronomers are still studying today. This event was the birth of the Vela Pulsar. To understand the enormity of what happened, imagine a star at least 8 to 20 times the mass of our Sun. For millions of years, it shone brilliantly, fusing lighter elements into heavier ones deep in its core. But once the fusion of iron began, the star was doomed. No further energy could be generated to counterbalance the crushing force of gravity. Within seconds, its core collapsed, and the outer layers came crashing inward at speeds reaching a significant fraction of the speed of light. The result was an explosion so luminous that, had it occurred in today's skies, it would outshine everything else except the moon. For ancient humans, hunter-gatherers, shamans, and early tribes scattered across Earth, this event may very well have been visible. Imagine a bright star suddenly flaring into the night sky, a beacon that remained for weeks or months, dominating their view of the heavens. They had no telescopes or astrophysics to explain it, but they would have seen something extraordinary. Some researchers suggest that ancient rock art and oral traditions might contain echoes of such cosmic spectacles, though no direct evidence ties prehistoric accounts specifically to the Vela supernova. Still, the thought that our ancestors once gazed in or at the birth of the Vela Pulsar connects us to this event in a deeply human way. The aftermath of that supernova is still visible today as the Vela supernova remnant, an enormous shell of expanding gas and dust, tangled with shock waves and filaments glowing in multiple wavelengths of light. This remnant spans over 100 light-years across and appears to cover a large portion of the sky when observed with radio and X-ray telescopes. Its tendrils of gas are rich with heavy elements like oxygen, silicon, and iron, the raw materials that will one day be recycled into new stars, planets, and perhaps even life. In this way, the death of the Vela progenitor star was also an act of creation, seeding the cosmos with the building blocks of future worlds. At the center of this cosmic debris field lies the compact remnant, the Vela Pulsar. During the collapse, the star's core was squeezed into a neutron star about 20 kilometers in diameter, with a mass greater than that of our Sun. The conservation of angular momentum meant that as the star shrank, it spun faster and faster, ultimately reaching a rotation rate of 11 times per second. The intense magnetic fields amplified by the collapse became the channels through which beams of radiation would shoot out into space. What had once been the beating heart of a giant star was reborn as a cosmic lighthouse, its rhythm detectable across thousands of light-years. The supernova that birthed Vela was also a source of extreme cosmic energy. The blast released neutrinos, ghostly particles that rarely interact with matter, in quantities so vast that for a brief moment, they carried away the majority of the energy of the explosion. These neutrinos streamed through the universe, passing effortlessly through everything in their path, including the Earth. If humanity had the technology at that time, we could have detected trillions upon trillions of these particles passing right through our bodies in the aftermath of the event. The shockwave from the explosion continues to ripple through space even now. It interacts with interstellar gas, heating it up, compressing it, and creating rippling arcs of emission that telescopes can see in exquisite detail. Observations with X-ray observatories such as Chandra have revealed complex structures in the Vela supernova remnant, loops, filaments, and knots of matter still glowing thousands of years after the initial blast. It is one of the closest and best-studied remnants of its kind, offering astronomers a cosmic laboratory to test models of supernova explosions. For us, the Vela supernova is a reminder of both the fragility and the power of stars. These titanic explosions are responsible for much of the chemical richness of the universe. The calcium in our bones, the iron in our blood, the oxygen we breathe, all forged in the furnaces of massive stars and scattered across the cosmos in supernovae. The Vela event, in particular, would have spread such elements into the surrounding interstellar medium, contributing to the ongoing cycle of stellar birth and death in our galaxy. What makes Vela's origin especially fascinating is that we can still observe both pieces of its legacy: the remnant cloud that testifies to the explosion itself, and the pulsar at the center that is the surviving core of the dead star. Together, they tell a complete story, one of catastrophic death, transformation, and enduring mystery. The supernova origin of the Vela Pulsar sets the stage for everything that makes it unique today. Without that explosive beginning, there would be no rapidly spinning neutron star, no pulses of light, no glitches, and no nebula energized by its winds. The event that ancient humans might have seen as a blazing point of light in their night sky continues to echo across space and time, reaching us not just as visible remnants but also as signals that help us probe the universe's most extreme physics. And now, knowing the explosive birth that brought the Vela Pulsar into being, we can turn our focus to one of its most striking characteristics: its incredible speed of rotation, a dizzying spin that challenges our intuition about what matter can endure under the crushing grip of gravity. The Vela Pulsar's supernova origin is already an awe-inspiring tale, but what it left behind is even more staggering when we take a closer look at how fast this remnant spins. The Vela Pulsar rotates at a rate of about 11 times per second. To a casual listener, that number may not sound extraordinary, but when we break it down and compare it to familiar scales, the reality becomes almost incomprehensible. Let's begin with Earth. Our planet completes one rotation in 24 hours. That's one leisurely spin every 86,400 seconds. Now, picture the Vela Pulsar, an object only about 20 kilometers in diameter, roughly the size of a small city, spinning 11 times every single second. In 1 minute, it has rotated 660 times. In an hour, nearly 40,000 times. In the time it takes Earth to complete one slow, steady day-long rotation, Vela has already completed close to 1,000,000 spins. This comparison highlights the extreme difference between our everyday sense of motion and the realities of neutron stars. Earth's equator rotates at a speed of about 1,670 km per hour due to its daily spin. The Vela Pulsar, on the other hand, is moving its surface at an astonishing 70,000 km per hour or more, depending on the exact radius we assume. That's about 20 times faster than a bullet fired from a rifle, and yet this speed is not only sustainable, it is stable, maintained for thousands of years since its birth. But what makes this even more incredible is the fact that Vela is not unique in spinning fast. Many pulsars do. Some millisecond pulsars rotate hundreds of times per second, breaking all intuitive limits of motion. Still, Vela's speed is special because of its youth and its unique behaviors, such as glitches, which we'll discuss soon. At 11 rotations per second, Vela falls into the category of relatively young pulsars, which often spin faster than their older counterparts. Over time, pulsars slow down as they lose energy, but Vela remains a vibrant and energetic star, its rotation still dizzyingly quick. The speed of the Vela pulsar is a direct consequence of the conservation of angular momentum during its birth. Think of a figure skater. When they pull in their arms, their rotation speed increases dramatically. Now imagine that figure skater as a star many times the mass of our Sun. As the massive outer layers collapse inward during the supernova, the core shrinks from millions of kilometers across to just a few tens of kilometers. The rotation that was once relatively slow suddenly becomes blindingly fast. It is physics at its most extreme. And here's another layer of the mystery. Not only does Vela spin rapidly, but it does so with remarkable precision. Each rotation produces pulses of radiation that reach us with timing so regular that, in most cases, pulsars can rival atomic clocks. This means that while it is spinning furiously fast, it is also spinning consistently, like a perfectly engineered machine. The pulsar's rotation is so steady that astronomers use pulsars to study phenomena such as the warping of spacetime and the detection of gravitational waves. The precision with which these stars spin is one of their defining features, and Vela exemplifies this paradoxical combination of chaos and order, born from a violent explosion, yet operating like a cosmic metronome. However, Vela does not always remain perfectly predictable. While it usually ticks away with astonishing regularity, there are sudden moments when it changes pace, speeding up in what astronomers call a glitch. These glitches set Vela apart from most other pulsars and provide one of the greatest opportunities to probe what's really happening inside neutron stars. But before we explore those glitches, it's worth reflecting once more on the raw extremes of this star's spin. Imagine holding a ball the size of a city in your mind's eye, but instead of moving gently, that ball is rotating faster than the blades of a helicopter or the turbines of a jet engine. Now compress the mass of the Sun into that object. The forces at play are so intense that if Vela were any larger or spinning much faster, it might tear itself apart. The fact that it holds together speaks to the extraordinary strength of neutron star matter, a state of matter so dense that the very concept challenges our understanding of physics. For scientists, the Vela pulsar's rotation is more than just an impressive number. It is a living experiment in how matter behaves under pressures we can't reproduce. It is a demonstration of physics operating under the most extreme conditions in the universe. Every pulse we receive from Vela is like a signal that carries information about its spin, its energy, and the forces deep inside it that we still cannot fully explain. As extraordinary as this rotational speed is, the Vela pulsar is far from being a perfectly stable cosmic machine. Its spin occasionally betrays its secrets through sudden changes. These are the glitches, moments when the pulsar unexpectedly jumps to a higher speed of rotation. What could possibly cause such a dense, stable, and precise object to hiccup? The answer lies not on its surface but deep inside, in the strange and exotic interior of the neutron star. And that is where the mystery of the Vela pulsar deepens further. While the Vela pulsar's dizzying rotation is impressive in itself, it is its glitches that truly set it apart and make it one of the most enigmatic stars in the galaxy. Glitches are sudden, unpredictable increases in a pulsar's rotational speed, a phenomenon that has fascinated astronomers for decades. Unlike the steady ticking of most pulsars, which act like precise cosmic clocks, Vela occasionally appears to skip a beat, or rather, to speed up a beat, before settling back into its regular rhythm. These events are not merely minor variations. They represent tangible, measurable changes in the behavior of one of the densest objects in the universe, providing a unique glimpse into its otherwise invisible interior. The discovery of glitches in the Vela Pulsar came as a surprise to astronomers. Pulsars had initially been celebrated for their incredible regularity, with pulses arriving so predictably that some were even used as tools to measure astronomical distances and test theories of general relativity. Vela, however, demonstrated that even these perfect clocks were not immune to internal upheaval. During a glitch, the pulsar can increase its rotation rate by a tiny fraction, often just a few parts per million, but because the pulses are so precisely timed, even such small changes are instantly detectable. It's as if a finely tuned metronome suddenly skips a beat, giving a subtle hint that something extraordinary is happening inside. The frequency and magnitude of Vela's glitches are particularly notable. While many pulsars might experience minor glitches only occasionally over decades, Vela glitches relatively frequently, sometimes every few years. When these glitches occur, the change in rotational speed is measurable and abrupt. For astronomers, this is a rare opportunity. It is one of the few ways to probe the hidden interior of a neutron star. Unlike stars like the Sun, where we can observe the surface directly, a neutron star is opaque. We cannot see inside it. But glitches act like seismic tremors, sending clues to the surface about the exotic physics taking place deep within. What causes a glitch? While the exact mechanisms remain a subject of active research, scientists have developed several theories. One of the leading explanations involves superfluidity within the star. In normal matter, particles interact and collide, generating friction. But in a neutron star, the neutrons in the inner layers may exist in a superfluid state, a frictionless, quantum form of matter that flows without resistance. Over time, the outer crust of the star gradually slows due to the emission of electromagnetic radiation, while the inner superfluid continues spinning faster. Eventually, this superfluid can transfer angular momentum suddenly to the crust, causing the outer layers to catch up almost instantaneously. The result is a glitch. The pulsar's rotation speeds up, seemingly without warning. Another contributing factor may involve the rigid crust of the neutron star itself. The crust, though incredibly dense, can experience stress as the star loses energy and slows down. The interior superfluid and the crust are coupled in complex ways. When the stress becomes too great, the crust may fracture or shift slightly, releasing stored angular momentum into the star's rotation. This could produce a sudden acceleration, a glitch, before the system gradually relaxes back into a predictable rhythm. Vela's glitches are especially important because they are among the largest and most frequent observed in any pulsar, providing a wealth of data for theorists. Observatories around the world, including large radio telescope arrays, monitor Vela's pulses constantly, waiting for the next glitch. When one occurs, it offers a rare chance to study how neutron stars behave under conditions that cannot be replicated on Earth. Immense density, magnetic fields trillions of times stronger than the Sun's, and rotation rates that push matter to its physical limits. Each glitch becomes a probe of extreme physics, a brief crack in the outer surface that lets us infer what lies beneath. Interestingly, glitches do not occur randomly in all pulsars. They are often associated with younger, faster spinning stars. Vela, at roughly 11,000 to 12,000 years old, fits this profile perfectly. Its youth, combined with its rapid spin and powerful magnetic fields, creates the ideal conditions for these sudden rotational anomalies. This is why Vela is sometimes described as the poster child for pulsar glitches, and why decades of observations have focused so heavily on it. Beyond their scientific importance, glitches also highlight the paradoxical nature of pulsars. On one hand, Vela spins with astonishing regularity, its pulses arriving like clockwork across space. On the other hand, these glitches remind us that beneath this apparent perfection lies a violent, restless interior, matter in forms that challenge our understanding, behaving according to laws of physics we cannot fully reproduce in the laboratory. The pulsar is at once predictable and capricious, orderly and chaotic, a cosmic paradox that continues to intrigue researchers. Glitches are also a window into the long-term evolution of neutron stars. By studying how the frequency and magnitude of glitches change over time, scientists can estimate the age of the pulsar more accurately and model how angular momentum is transferred from the superfluid core to the crust. This knowledge informs not only our understanding of Vela but also of other pulsars and the general behavior of neutron stars in our galaxy. Ultimately, the Vela pulsar's glitches are not just quirks, they are a signature of the exotic physics operating at its core. They hint at a reality where matter behaves in ways utterly alien to our experience, where quantum mechanics, relativity, and nuclear physics collide in a single, spinning object. Observing a glitch is like catching a whisper from the hidden heart of the universe, a reminder that even the most precise cosmic clocks can surprise us. Having explored the nature of Vela's glitches, we can now delve into why these events matter so profoundly, what they reveal about the inner workings of neutron stars, and why astronomers around the world pay such close attention to every subtle shift in Vela's rotation. The Vela pulsar's glitches are far more than a curious oddity. They are a window into the hidden depths of one of the universe's most extreme objects. To understand why they matter, it is essential to recognize that neutron stars are unlike anything else in nature. Composed almost entirely of neutrons packed to densities so extreme that a sugar cube-sized amount would weigh billions of tons, these stars are laboratories of matter under conditions that cannot be replicated on Earth. Their interiors exist in states that push the limits of nuclear physics, and the glitches observed in Vela provide one of the very few ways to probe these exotic interiors. When the Vela pulsar suddenly speeds up during a glitch, it is not simply misbehaving for the fun of it. These rotational jumps are intimately connected to the physics of the star's interior. The most widely accepted explanation involves the presence of superfluid neutrons deep inside the star. A superfluid is a state of matter in which particles flow without friction, a phenomenon predicted by quantum mechanics and observed in laboratory experiments with liquid helium. In a neutron star, the pressures are so immense that vast regions of the interior, potentially including the inner crust and core, may exist in this superfluid state. Superfluidity inside the neutron star allows the inner layers to rotate at a slightly different rate than the outer crust. The crust, though only a few kilometers thick, is rigid and experiences gradual slowing due to electromagnetic radiation emitted as the pulsar spins. Meanwhile, the superfluid interior retains much of its angular momentum. Over time, a mismatch develops between the faster spinning core and the slower spinning crust. When this imbalance reaches a critical point, angular momentum is suddenly transferred from the superfluid to the crust, producing the abrupt increase in rotation we observe as a glitch. In essence, every glitch is a signal from the hidden layers beneath the crust, giving astronomers a rare glimpse into the behavior of matter under extreme densities. Since we cannot directly probe the interior of a neutron star, these glitches serve as natural experiments, revealing how superfluids, nuclear matter, and the rigid crust interact. Observations of glitches, especially in a well-monitored pulsar like Vela, allow physicists to refine models of superfluid dynamics and understand how quantum effects operate on a scale billions of times larger than anything we can create in a lab. Glitches also provide crucial information about the structural composition of neutron stars. By measuring the magnitude and frequency of these sudden jumps, scientists can infer properties of the crust, such as its thickness, rigidity, and how it couples to the superfluid interior. Larger glitches suggest that significant angular momentum is being stored in the inner layers before release, while smaller glitches may indicate subtler transfers. Over time, these observations have led to models in which the crust and inner superfluid are delicately balanced in a dynamic, ongoing exchange, a delicate cosmic choreography invisible to even the most powerful telescopes, yet revealed through Vela's pulses. Moreover, glitches help us probe the extreme physics of nuclear matter. At densities exceeding those of atomic nuclei, the behavior of neutrons and protons is poorly understood. Different theoretical models predict variations in how neutrons interact, how superfluid vortices behave, and how angular momentum is transferred. By analyzing glitches in Vela, astronomers can compare real-world data with these models, ruling out some possibilities and refining others. Essentially, every glitch is a data point in one of the most extreme physics experiments imaginable. Nature itself running a laboratory experiment with a neutron star as the apparatus. Interestingly, Vela's glitches are also telling us about the evolutionary life cycle of young pulsars. Younger pulsars tend to glitch more frequently, suggesting that their crusts and superfluid interiors are still adjusting to the rapid spin-down caused by radiation. Over time, as the pulsar ages and loses rotational energy, glitches become less frequent. By studying Vela, astronomers gain insight into how neutron stars age, how their interiors evolve, and how their rotation and magnetic fields gradually change over millennia. Beyond the physics of superfluids and crustal structure, glitches have implications for astrophysical models of neutron star populations. Observing the frequency and size of glitches helps astronomers estimate the distribution of rotational energies among pulsars in our galaxy, and it informs simulations of how neutron stars interact with their environments. For example, the energy released during a glitch slightly alters the pulsar wind and surrounding nebula, affecting the dynamics of the Vela supernova remnant. In this way, even tiny, rapid changes inside the pulsar can ripple outward, influencing the surrounding space over thousands of years. Glitches also remind us that pulsars are living records of extreme physics. They encode information about quantum mechanics, nuclear forces, and superfluid behavior on a scale that is impossible to replicate in a laboratory. Each sudden spin up is a message from the pulsar's interior, a way for this distant, dense object to communicate directly with us across light years. By carefully monitoring Vela, astronomers are learning not only about the pulsar itself but also about the fundamental laws of nature under conditions that push every theory to its limit. In summary, Vela's glitches matter because they are much more than curiosities. They are cosmic probes of the invisible interior of neutron stars. They allow us to study superfluids at nuclear densities, understand the structure and evolution of ultra-dense matter, and refine models of how these exotic stars function over time. The combination of precision rotation and sudden unpredictability makes Vela a paradoxical teacher, orderly and chaotic, constant yet intermittent, predictable in its pulse yet revealing deep secrets in its sudden disruptions. Having established why these glitches are so significant, the next step is to look at the pulsar's pulses of light themselves, the steady beacons that allow astronomers to detect these phenomena in the first place. These pulses are not just a measure of time. They are the medium through which we witness the extreme physics of Vela at work. The Vela pulsar's glitches are compelling evidence of the extraordinary physics hidden deep within its interior, but they are only part of the story. Equally remarkable are the pulses of light that sweep across the cosmos like a cosmic metronome, reaching Earth with uncanny regularity. These pulses are what first alerted astronomers to the existence of pulsars, and they remain one of the most fascinating and useful features of the Vela pulsar today. They are not merely light in the conventional sense, they are intense beams of electromagnetic radiation, spanning radio waves, X-rays, and gamma rays, emanating from a star smaller than a city yet packing more mass than the Sun. To understand these pulses, we must remember that the Vela pulsar is a neutron star with a strong magnetic field that is misaligned with its rotational axis. This misalignment is crucial. It ensures that the beams of radiation are not constant in every direction, but instead sweep across space in a circular arc as the star rotates. Picture a lighthouse on a distant shore. The light does not illuminate the entire ocean at once but rotates in a fixed arc, flashing periodically in the direction of the observer. For Vela, Earth lies in the path of one of these beams. Every time the pulsar rotates, its beam crosses our line of sight, producing the characteristic pulse that telescopes detect. These pulses are astonishingly precise. In some pulsars, a single pulse may arrive within a fraction of a millisecond of the predicted time, even after traveling over 1,000 light-years. This precision rivals, and in some cases exceeds, the accuracy of the best atomic clocks on Earth. The consistency of Vela's pulses is remarkable given the violent and chaotic processes that created it. A star that exploded violently in a supernova, collapsed into a neutron star, and now spins 11 times per second while radiating enormous amounts of energy. That such a system can produce a steady, predictable signal over millennia is a testament to the unique stability of neutron stars and their magnetic fields. The beams themselves are generated by a combination of factors. As the neutron star spins, charged particles near the magnetic poles are accelerated to near-light speeds along magnetic field lines. These particles emit radiation through mechanisms such as synchrotron radiation and curvature radiation, creating a focused beam that shoots into space. The intensity of the radiation depends on the spin rate, the strength of the magnetic field, and the configuration of the field lines. Vela's beam is exceptionally strong, which is why it is one of the brightest pulsars in both radio and high-energy wavelengths. Astronomers detect these pulses using highly sensitive radio telescopes and space-based observatories. By recording the timing of each pulse, scientists can monitor the pulsar's rotation, detect glitches, and even study the intervening interstellar medium. The regularity of Vela's pulses allows for extremely precise measurements. Tiny deviations in pulse arrival times can indicate changes in the pulsar's rotation, the presence of orbiting companions, or even ripples in spacetime, like gravitational waves. In this sense, the pulses are not just a light show, they are a tool for cosmic exploration, carrying information about the pulsar itself and the space between stars. Another fascinating aspect of Vela's pulses is their multi-wavelength nature. While radio pulses are the easiest to detect from Earth, Vela also emits strong X-ray and gamma-ray pulses. Observations in these high-energy bands have revealed structures around the pulsar, such as jets and arcs, powered by its rotational energy. Each pulse in these bands corresponds to a burst of particles traveling near the speed of light, producing radiation that illuminates the surrounding nebula. These high-energy pulses provide complementary information to radio observations, allowing astronomers to map both the pulsar's magnetic field and the energetic environment it creates. The precision of these pulses is not just scientifically valuable, it is also philosophically profound. Here is an object born from one of the most violent events in the universe, a supernova explosion, yet it produces a signal of astonishing regularity that can be measured thousands of light-years away. Each pulse is a heartbeat from a collapsed star, a rhythm maintained over millennia, impervious to the chaos that created it. This combination of violence and precision, unpredictability and order, makes the Vela Pulsar one of the most mesmerizing objects in the sky. Importantly, the pulses are also the mechanism that alerts us to other phenomena, such as pulsar winds. The energy carried in these beams and the associated particle emissions generates shockwaves and energizes the surrounding supernova remnant. Without these pulses, we might detect the Vela Pulsar as little more than a faint point in the sky. Instead, they allow us to trace its influence across light-years of space, revealing interactions between the pulsar and the surrounding interstellar medium. In summary, Vela's pulses of light are both signal and story. They tell us about the star's spin, its magnetic field, its superfluid interior, and the energetic environment it creates. They allow astronomers to measure time across cosmic distances with unmatched accuracy, study the most extreme states of matter, and detect minute changes in the star's behavior. Each pulse is a heartbeat from a star that has survived its own death, a signal that has traveled over 1,000 years to reach our instruments, and a reminder of the extraordinary precision inherent in the natural universe. With these pulses serving as our primary messenger, astronomers have also turned their attention to the Vela Pulsar's surrounding nebula, where the energy from these beams interacts with the remnants of the supernova explosion. It is here, in the cloud of charged particles and shockwaves known as the Pulsar Wind Nebula, that the star's power becomes visible on a grand, cosmic scale. The Vela Pulsar is not just a rapidly spinning neutron star sending precise pulses of radiation across space, it is also the central engine powering one of the most fascinating and dynamic structures in the sky, the Pulsar Wind Nebula, PWN. Surrounding Vela is an intricate cloud of charged particles, high-energy radiation, and shockwaves collectively known as the Vela Pulsar Wind Nebula, a structure that extends light-years into space and reveals the extraordinary interaction between the pulsar and its environment. Studying this nebula is akin to watching the physical manifestation of the pulsar's energy as it sculpts its cosmic surroundings. At the heart of the nebula is the pulsar itself, spinning 11 times per second and emitting beams of radiation and a steady flow of particles. These particles, mostly electrons and positrons, are accelerated to nearly the speed of light by the pulsar's immense magnetic field. The energy driving this particle wind comes from the rotational energy of the neutron star itself. Essentially, the pulsar is gradually slowing down as it converts its spin into energetic outflows. When these high-energy particles slam into the surrounding gas left over from the supernova explosion that birthed Vela, they generate shockwaves and synchrotron radiation, creating glowing structures that are visible across multiple wavelengths. The Vela Pulsar Wind Nebula is highly structured, exhibiting arcs, jets, and filaments that appear almost artistic in nature but are, in fact, the result of complex interactions governed by physics at extremes unattainable on Earth. The inner region closest to the pulsar contains termination shocks, boundaries where the pulsar wind collides with slower-moving supernova debris. Here, particles are accelerated to even higher energies, producing bright X-ray emission that space telescopes like Chandra can detect. These X-ray structures trace the geometry of the pulsar's magnetic field, revealing twisted, spiral-like formations and narrow jets extending from the poles. Observing these features allows astronomers to map the flow of energy from the pulsar into the nebula in 3 dimensions. Beyond the immediate vicinity of the pulsar, the wind spreads outward, interacting with older, slower-moving material ejected during the supernova explosion. These interactions create filaments and arcs visible in radio and optical wavelengths. The filaments are composed of charged particles spiraling along magnetic field lines, glowing through synchrotron radiation. Their shapes are not random, they are sculpted by the balance of pressure, magnetic fields, and the momentum of the pulsar wind. The resulting structure is both chaotic and organized, a visual record of energy transfer across thousands of years. One of the most fascinating aspects of the Vela Pulsar wind nebula is its dynamic behavior. Observations over time have shown that certain features within the nebula, such as jets or wisps of high-energy particles, can move or evolve on timescales of months or years. This is extraordinary when considering that the material is light-years away from the pulsar and is traveling at relativistic speeds. The nebula is, in essence, alive, continuously shaped by the pulsar's rotational energy and magnetic fields, giving astronomers a rare opportunity to study real-time physics on cosmic scales. The nebula also provides insight into the energy budget of the pulsar. By measuring the luminosity and extent of the nebula in different wavelengths, scientists can estimate how much rotational energy the pulsar is losing over time and how efficiently it is converted into particle acceleration. For Vela, this energy is immense. The pulsar's spin-down power, the rate at which it loses rotational energy, is on the order of 10 to the power of 36 ergs per second, enough to energize the surrounding nebula and generate radiation brighter than entire star clusters in certain wavelengths. Essentially, Vela is continuously pouring energy into its environment, keeping the nebula glowing and dynamic thousands of years after the supernova explosion. Another remarkable feature of the nebula is its interaction with the supernova remnant itself. The Vela supernova remnant is an expansive shell of gas and dust, still expanding after the explosion that created the pulsar. The pulsar wind collides with this material, creating regions of turbulence and heating. In some areas, this interaction forms bow shocks, where the fast-moving pulsar wind slams into slower debris, producing sharp, curved structures. Observing these bow shocks allows astronomers to study the dynamics of high-energy plasma in a unique environment, where relativistic particles, magnetic fields, and dense matter interact simultaneously. Studying the Vela Pulsar wind nebula also provides critical clues about how pulsars affect the broader galaxy. Pulsars like Vela inject enormous amounts of energy into their surroundings, influencing the temperature, density, and magnetic structure of the interstellar medium. This feedback can trigger or suppress star formation in nearby regions, showing that even a small neutron star, barely 20 kilometers across, can have a profound impact across dozens of light-years. The nebula is thus both a local laboratory for extreme physics and a key component of galactic ecology. In addition, the Pulsar Wind Nebula is a gamma-ray powerhouse. High-energy electrons and positrons in the nebula interact with photons and magnetic fields, producing gamma rays that make Vela one of the brightest gamma-ray sources in the sky. These emissions are critical for understanding particle acceleration at relativistic speeds. They also connect Vela to broader questions in astrophysics, such as the origin of cosmic rays and the mechanisms by which compact objects distribute energy into their environment. In summary, the Vela Pulsar Wind Nebula is a dynamic, luminous, and high-energy environment directly powered by the pulsar's spin. It is a multi-wavelength spectacle of arcs, jets, filaments, and shockwaves that maps the flow of energy from one of the universe's densest objects into the surrounding remnants of a supernova. The nebula is not merely a halo of light, it is a living record of energy transfer, particle acceleration, and magneto-hydrodynamic processes operating under conditions far beyond anything found on Earth. Through careful observation of this nebula, scientists gain insight into the pulsar itself, its history, and the extraordinary forces that govern the cosmos. Having explored the complex environment of the Pulsar Wind Nebula, we can now focus on the Vela Pulsar as an extraordinary cosmic energy source, revealing just how powerful this compact star truly is and why it continues to shine so brightly across the universe. The Vela Pulsar is not only remarkable for its precise pulses and its dynamic wind nebula, it is also one of the most powerful cosmic energy sources in the sky, particularly in the high-energy regime of gamma rays. Among all known pulsars, Vela stands out as one of the brightest gamma-ray emitters, producing radiation that can outshine even entire distant galaxies at these extreme energies. This makes it a fundamental object for astrophysicists seeking to understand the mechanisms of energy generation and particle acceleration under the most extreme conditions in the universe. Gamma rays are the most energetic form of electromagnetic radiation, with energies millions to billions of times higher than visible light. The fact that a neutron star only 20 kilometers across can produce such an immense flux of gamma rays is extraordinary. This emission is powered by the rotational energy of the pulsar, which is gradually converted into radiation and kinetic energy of particles. Essentially, the Vela Pulsar is spinning down, losing a fraction of its rotational energy every second. That energy manifests as gamma rays, X-rays, and a pulsar wind of high-speed particles, making the pulsar a highly efficient cosmic engine. The gamma-ray emission from Vela is primarily generated in the magnetosphere, the region surrounding the neutron star dominated by its intense magnetic field. Charged particles, electrons and positrons, are accelerated along magnetic field lines to speeds approaching the speed of light. As they curve along these lines, they emit curvature radiation, which produces photons in the gamma-ray energy range. Additional gamma rays result from inverse Compton scattering, where the accelerated particles transfer energy to lower energy photons, boosting them into the gamma-ray regime. The result is an incredibly bright, high-energy beam of radiation emanating from the magnetic poles of the pulsar. What is particularly striking is Vela's relative brightness compared to extragalactic sources. When viewed from Earth using gamma-ray observatories like NASA's Fermi Gamma Ray Space Telescope, the Vela Pulsar is often among the most prominent sources in the sky, despite being only 1,000 light-years away, a mere stone's throw in galactic terms. By contrast, many distant galaxies emit gamma rays from billions of stars, supernovae, and black hole activity. Yet Vela, a single neutron star, can rival or even surpass these sources in intensity. This highlights both its efficiency and the sheer scale of energy concentrated in a tiny object. Vela's high energy output is not only impressive in magnitude but also highly directional, linked to the pulsar's rotation. As the neutron star spins, the gamma-ray beam sweeps across the sky. From Earth, we see periodic flashes, which are the signature pulses of radiation. These pulses are critical for scientific study because they allow astronomers to measure not only the rotational properties of the pulsar but also the geometry of its magnetic field and the mechanisms of particle acceleration in the magnetosphere. By studying the timing and energy distribution of these gamma-ray pulses, researchers can infer details about how the pulsar converts rotational energy into high-energy radiation with such remarkable efficiency. Another remarkable aspect of Vela's gamma-ray emission is its consistency. Despite its powerful output, the pulsar maintains a predictable pattern of pulses, allowing astronomers to use it as a probe of extreme physics. The stability of its gamma-ray pulses, except for glitches in rotation, means that even a chaotic, high-energy system can operate with extraordinary precision. This combination of immense energy and regularity makes Vela both a powerhouse and a precise cosmic clock. The pulsar's gamma rays also feed the surrounding pulsar wind nebula, energizing electrons and positrons that radiate across the electromagnetic spectrum. The interaction of these high-energy particles with magnetic fields and leftover supernova debris produces X-rays and radio emissions, creating a multi-wavelength halo that maps the pulsar's influence over light-years of space. Essentially, the gamma-ray emission is the primary energy source that powers the nebula, demonstrating how the rotational energy of a single neutron star can have a galaxy-scale impact. Vela's role as a cosmic energy source also provides an important laboratory for testing theories of high-energy astrophysics. Understanding how a neutron star generates gamma rays at such intensities allows scientists to explore phenomena like particle acceleration in extreme magnetic fields, the behavior of matter under near-light speed conditions, and the interactions between relativistic winds and interstellar material. In effect, the Vela Pulsar is a natural particle accelerator operating far beyond anything achievable on Earth, providing a window into processes that govern the most energetic events in the universe. In broader astronomical terms, the energy emitted by Vela helps calibrate our understanding of other pulsars and high-energy sources. By comparing Vela to fainter or more distant pulsars, scientists can construct models of how rotational energy, magnetic fields, and superfluid interiors combine to produce observable radiation. In this way, Vela serves as a benchmark, a luminous reference point against which the behavior of other neutron stars can be measured. Ultimately, Vela's gamma-ray luminosity underscores the dual nature of pulsars. They are both extremely small and extraordinarily powerful, compact objects whose influence extends across light-years of space. Its energy output is a constant reminder that neutron stars are far from inert. They are engines of transformation, converting rotation into radiation and sculpting the environment around them. By observing this energy, we gain insight into the physics of the universe at its most extreme, from the quantum behavior of superfluid interiors to the vast scale of galactic particle acceleration. With this understanding of Vela as a cosmic powerhouse, we can now explore its broader astronomical importance, examining how studying this extraordinary star allows scientists to test fundamental laws of physics and gain insights that reach far beyond the immediate neighborhood of our galaxy. The Vela Pulsar is far more than a remarkable cosmic light source or a spectacular display of high-energy radiation. It is a laboratory for extreme physics. Studying Vela allows scientists to probe conditions that are utterly inaccessible on Earth, from the densest forms of matter to the most powerful magnetic fields in the universe. Its astronomical importance stems not just from its brightness or proximity, but from the fact that it is one of the most accessible examples of a neutron star, a type of object that pushes the limits of our understanding of physics. At the heart of Vela's significance is its ultra-dense interior. Neutron stars, including Vela, are composed predominantly of neutrons packed so tightly that a sugar cube-sized piece of their material would weigh billions of tons. These densities exceed those found in atomic nuclei, creating conditions that cannot be replicated in laboratories on Earth. By observing Vela's rotation, pulses, and glitches, scientists can make inferences about how matter behaves at these extreme densities. In particular, the combination of steady pulsation and sudden glitches offers a unique window into the interaction between the rigid crust and the superfluid core, revealing insights into quantum phenomena on macroscopic scales. One of the most important areas of research that Vela contributes to is nuclear physics under extreme conditions. The structure of the neutron star, its equation of state, the relationship between pressure, density, and temperature in its interior, and the properties of superfluid neutrons are all directly constrained by observations of pulsars like Vela. For instance, the size and frequency of glitches provide information about how angular momentum is stored and transferred within the star, shedding light on the mechanics of matter at nuclear densities. These observations help scientists refine models of the strong nuclear force, the fundamental interaction that holds atomic nuclei together, under conditions far more extreme than any terrestrial experiment can achieve. Vela also provides a testbed for magneto-hydrodynamics in extreme regimes. Its magnetic field is trillions of times stronger than Earth's, and the interplay between rotation, magnetic field, and charged particles creates complex behaviors such as pulsar winds, high-energy beams, and shocks in the surrounding nebula. Observing how the pulsar channels energy into its environment allows astrophysicists to study plasma behavior at relativistic speeds, energy dissipation, and particle acceleration under conditions that defy classical physics. In essence, Vela allows scientists to see nature operating on a scale that is both fantastically small and fantastically energetic at the same time. The precision of Vela's pulses also has profound implications for fundamental physics and cosmology. Because the pulses are so regular, astronomers can use them to measure extremely subtle effects, such as tiny changes in rotational speed, gravitational interactions with surrounding material, or the propagation of radiation through the interstellar medium. In some cases, pulsars like Vela are used to test Einstein's theory of general relativity, particularly in how gravity affects the timing of signals over large distances. Small deviations in pulse arrival times can provide information about gravitational waves, space-time curvature, or the presence of otherwise invisible objects in the pulsar's neighborhood. The Vela Pulsar also helps scientists study the life cycle of massive stars and stellar remnants. By comparing the pulsar's current rotation, magnetic field, and glitch behavior with models of neutron star evolution, astronomers can trace back its history to the original supernova explosion and predict how it will continue to evolve over thousands to millions of years. This provides valuable insight into the broader population of neutron stars and how these exotic objects influence their surroundings, from energizing supernova remnants to producing cosmic rays. Moreover, Vela's proximity, only about 1,000 light-years away, makes it an ideal target for multi-wavelength observations. Unlike more distant neutron stars, Vela can be observed in radio, X-ray, and gamma-ray wavelengths simultaneously, offering a complete picture of the pulsar's behavior and its interactions with the surrounding nebula. Each wavelength reveals different aspects of the physics at play. Radio pulses trace rotational dynamics, X-rays reveal the structure of the inner nebula and particle acceleration, and gamma rays illuminate the highest energy processes occurring near the magnetic poles. This holistic view allows astronomers to cross-check models and understand extreme physics with unprecedented accuracy. Vela also acts as a bridge between microphysics and astrophysics. While experiments on Earth allow scientists to study atomic nuclei and quantum effects on small scales, Vela shows how these laws operate in objects many kilometers across under conditions of extreme density, pressure, and magnetic field strength. Observations of Vela and other pulsars help constrain theories of nuclear matter, superfluidity, and particle acceleration, providing a natural laboratory for physics that cannot otherwise be explored. Finally, Vela's glitches and pulses contribute to our understanding of the relationship between matter, energy, and time in extreme conditions. By tracking subtle variations in its rotation, astronomers can infer the behavior of matter in states where both relativistic effects and quantum mechanics are dominant. In other words, Vela allows scientists to explore how the fundamental laws of nature operate when pushed to their limits, bridging the gap between theoretical physics and observational astronomy. In summary, the astronomical importance of the Vela pulsar lies in its ability to act as a natural laboratory for extreme physics. From testing the behavior of matter at nuclear densities to probing superfluid dynamics, magnetohydrodynamics, and relativistic particle acceleration, Vela offers insights that are impossible to obtain anywhere else. Its pulses provide precise clocks, its glitches reveal hidden interiors, and its gamma-ray luminosity powers a nebula that illustrates the flow of energy on cosmic scales. By studying Vela, astronomers can confront some of the most profound questions in physics and astrophysics, making it a cornerstone of modern science. Having established why Vela is so critical to our understanding of extreme physics, we can now explore the paradoxical nature of its behavior, where its steady pulses operate like a clock while glitches introduce sudden, unpredictable jumps, a juxtaposition that continues to puzzle and fascinate scientists. The Vela pulsar presents one of the most fascinating paradoxes in astrophysics. It is at once a model of precision and a source of sudden chaos. On one hand, its pulses arrive with astonishing regularity, acting like a cosmic clock. On the other, it occasionally experiences sudden rotational glitches, unpredictable accelerations that defy its otherwise perfect rhythm. This duality, clockwork precision interrupted by spontaneous disruptions, makes Vela an enigmatic star, simultaneously reliable and mysterious, and provides scientists with some of the richest data in neutron star research. To appreciate this paradox, it is helpful to consider the nature of the pulsar's steady pulse first. As the Vela pulsar spins 11 times per second, its misaligned magnetic field generates beams of electromagnetic radiation that sweep across space. From our vantage point on Earth, these beams appear as pulses of light arriving with incredible regularity. For many pulsars, including Vela, the timing of these pulses can rival the accuracy of atomic clocks over short periods. For decades, astronomers have relied on these pulses to study everything from the interstellar medium to the fundamental properties of spacetime. The precision is extraordinary. Even after traveling 1,000 light-years, the pulse arrives at Earth at the predicted time to within microseconds. This reliability is why pulsars were initially likened to cosmic clocks. Each pulse acts like a tick of a timepiece, predictable and constant. Vela's pulse train is remarkably stable, providing a regular heartbeat that allows astronomers to measure rotational speed, monitor tiny slowdowns, and even search for minuscule distortions in spacetime caused by gravitational waves. In this sense, the pulsar seems perfectly ordered, a testament to the extreme stability of neutron star physics. Yet, this order is periodically disrupted by glitches. Unlike the smooth, gradual slowing of most pulsars due to energy loss, Vela occasionally experiences abrupt spin-ups, where its rotation rate suddenly jumps by a measurable fraction. These glitches are unpredictable, occurring without warning and interrupting the otherwise steady pulse pattern. While the increase in rotation is typically small, often just a few parts per million, the effect is unmistakable when monitored with the precision timing that pulsars afford. After a glitch, the pulsar slowly relaxes back toward its expected spin-down rate, as though recalibrating its cosmic clock. This juxtaposition, the coexistence of near-perfect regularity and abrupt irregularity, is what makes Vela such an extraordinary laboratory. On one level, the pulses reflect the mechanical stability of the neutron star. A dense crust, a fast-spinning superfluid interior, and a stable magnetic field working in harmony to produce predictable radiation. On another level, the glitches reveal dynamic processes occurring deep within, where superfluid neutrons suddenly transfer angular momentum to the crust or where stress fractures temporarily release stored rotational energy. The pulsar is both a machine of clockwork precision and a dynamic, restless object that occasionally breaks its own rhythm. The paradox also highlights the multilayered nature of neutron stars. The exterior, observed via pulses, appears calm and predictable. The interior, however, is a realm of extreme density and quantum behavior, containing superfluid matter that moves independently of the crust. Glitches are a window into this hidden interior. They occur when the inner superfluid suddenly couples to the crust, transferring angular momentum and producing a sudden spin-up. In effect, the predictable ticking we see is only a surface phenomenon. Beneath it lies a chaotic world of quantum fluids, extreme pressures, and violent interactions. This duality is scientifically invaluable. The steady pulse allows astronomers to establish baseline measurements, detecting even the smallest deviations in rotation or emission. Glitches, on the other hand, provide the contrast needed to probe extreme physics, revealing processes that cannot be measured under normal, stable conditions. By combining observations of both the clock-like pulses and the irregular glitches, scientists gain a more complete understanding of how neutron stars function, from crust dynamics and superfluid mechanics to magnetospheric behavior and particle acceleration. The paradox of Vela also has a poetic quality. It is a star born from an explosive supernova, yet it now behaves like a precise timekeeper. And yet, the memory of that violent birth manifests in glitches, subtle reminders that the pulsar's order is a fragile veneer over a fundamentally energetic and dynamic object. Each glitch interrupts the cosmic metronome, a fleeting glimpse of the violent processes still occurring deep within, while the pulse itself continues to tick steadily, unbroken over millennia. Furthermore, the interplay between clockwork and chaos demonstrates that neutron stars are not static remnants but active, evolving systems. They lose rotational energy, emit radiation, interact with surrounding matter, and periodically redistribute internal angular momentum. The Vela Pulsar exemplifies this duality: a stable, long-lived timer and a restless, energetic engine, simultaneously predictable and surprising. In practical terms, this combination of traits makes Vela an ideal natural laboratory. Its predictable pulses allow for precise astrophysical measurements, while glitches provide rare, high-value data about the superfluid core and the star's inner structure. Together, they allow scientists to test extreme physics that cannot be recreated on Earth: the behavior of matter at nuclear densities, the dynamics of superfluid vortices, and the transfer of angular momentum in an environment dominated by relativistic effects. Having considered this paradoxical behavior, the next logical step is to explore how Vela Pulsar serves as a laboratory for relativity, where both the steady ticking and sudden rotational anomalies allow researchers to test Einstein's theories under extreme conditions that push physics to its limits. Pulsars such as Vela are not only remarkable for their extreme density, rapid rotation, and enigmatic glitches, they are also extraordinary tools for probing the fabric of spacetime itself. The precision of their pulses makes them natural laboratories for testing Einstein's theory of relativity under conditions that are impossible to reproduce on Earth. While laboratories on our planet can test gravitational effects in small, controlled environments, pulsars provide cosmic-scale experiments, where gravity, rotation, and electromagnetic fields all interact at extremes that stretch the limits of our understanding. Einstein's general theory of relativity predicts that massive objects warp the spacetime around them. Neutron stars, with their immense mass concentrated into a tiny volume, create one of the most extreme gravitational environments in the universe outside of black holes. For Vela, this warping is significant but not so extreme that it hides the star entirely behind an event horizon. Instead, the pulsar sits in a regime where relativistic effects are strong enough to influence the timing of its pulses in measurable ways, offering a unique window into how matter and light behave under intense gravity. One of the key ways astronomers exploit this is through pulsar timing experiments. Each pulse from Vela can be predicted with astonishing accuracy, arriving at Earth within microseconds of expectation. By monitoring these pulses over months and years, Scientists can detect even minute deviations in arrival times. If space-time were warped or stretched by gravitational influences along the path from the pulsar to Earth, these tiny delays can be observed and measured. Vela's consistency allows researchers to distinguish between variations caused by the pulsar itself and those caused by the structure of space-time, effectively turning the pulsar into a precision probe of gravitational phenomena. Moreover, the Vela Pulsar's rapid rotation and extreme density mean that it produces gravitational fields much stronger than those encountered in typical astrophysical systems. This allows scientists to test predictions of general relativity in regimes far beyond solar system experiments, such as the bending of light, time dilation, and the propagation of gravitational energy. While Earth-based experiments can confirm general relativity to high precision in weak gravitational fields, pulsars like Vela push these tests to strong field limits, offering a more rigorous examination of Einstein's equations. The interaction between Vela's rotation, its magnetic field, and the surrounding supernova remnant also provides an indirect way to probe relativistic effects. High-energy particles moving near the speed of light, accelerated by the pulsar, experience relativistic time dilation and energy shifts. By observing the emission of X-rays and gamma rays from the pulsar and its nebula, scientists can study how relativistic effects influence particle trajectories, radiation beaming, and magnetic field interactions. Vela thus becomes a cosmic testbed not just for gravity, but for the interplay of relativity, electromagnetism, and high-energy particle physics. Another fascinating avenue is the potential use of pulsars like Vela in detecting gravitational waves, the ripples in spacetime first predicted by Einstein and confirmed a century later. By precisely timing the pulses from a network of pulsars, astronomers can search for correlated deviations caused by passing gravitational waves. While Vela alone cannot detect these waves, it is part of a broader array of pulsars that act collectively as a galactic scale detector. The reliability of Vela's pulses makes it a cornerstone in such experiments, providing a reference against which spacetime distortions can be measured. Vela also allows scientists to explore relativistic frame dragging and spin-orbit interactions in neutron stars. Because the pulsar spins so rapidly, the effects predicted by general relativity, such as the dragging of spacetime around the rotating mass, are more pronounced. Observations of pulse timing variations and the alignment of the pulsar's magnetic axis relative to its spin axis can provide indirect evidence for these effects, offering rare insights into how rotation and gravity intertwine in extreme objects. Even more subtly, Vela's glitches contribute to tests of relativity. When a pulsar suddenly accelerates during a glitch, it temporarily alters the gravitational influence it exerts on nearby space, however minutely. By carefully monitoring pulse arrivals before and after glitches, researchers can study whether sudden changes in rotation influence relativistic effects in ways consistent with theory. These observations push general relativity to its limits in conditions where quantum and nuclear effects also play a role, highlighting the complex interplay between the theory of gravity and the physics of ultradense matter. In essence, the Vela pulsar acts as a cosmic clock, particle accelerator, and gravity probe all at once. Its pulses provide a steady time reference, its high-energy emissions allow tests of relativistic particle physics, and its dense, spinning interior enables studies of gravity under conditions far more extreme than those accessible in any laboratory. Each observation contributes to a more complete understanding of how Einstein's theory operates when confronted with the universe's most energetic and compact objects. Through the study of Vela, scientists have confirmed that general relativity holds true even in these extreme regimes, while also identifying areas where observations challenge existing models and hint at new physics. In this way, Vela serves not only as a source of light and energy but also as a gateway to testing the fundamental laws of nature, connecting the cosmos to the theoretical frameworks that govern our understanding of reality itself. The understanding gained from these studies also feeds into broader questions, such as the potential detection of gravitational waves, the dynamics of neutron star mergers, and the behavior of matter at densities higher than atomic nuclei. In the next phase of exploration, this knowledge links directly to the search for ripples in spacetime caused by massive cosmic events, where monitoring pulsars like Vela may one day provide direct evidence of these elusive phenomena. The Vela pulsar's remarkable precision and predictable pulses do more than allow astronomers to study its own rotation or the physics of its interior. They also make it a potential tool for detecting gravitational waves, the ripples in spacetime predicted by Einstein and first confirmed in 2015 through the collision of black holes. Gravitational waves are produced by massive, accelerating objects, such as merging neutron stars, black holes, or asymmetric supernovae. As these waves propagate through the universe, they stretch and compress space-time ever so slightly. Detecting these tiny distortions requires extraordinarily precise timing instruments, and in this cosmic context, pulsars like Vela can act as natural detectors spanning thousands of light-years. The concept relies on what astronomers call pulsar timing arrays. By continuously monitoring the arrival times of pulses from multiple pulsars, scientists can look for correlated shifts caused by passing gravitational waves. If a wave passes between the pulsar and Earth, the distance that light must travel is minutely altered, causing the pulses to arrive slightly earlier or later than expected. These deviations are incredibly small, often on the order of tens of nanoseconds, but because pulsars like Vela emit pulses with extraordinary regularity, these tiny changes are detectable over long periods. Vela is particularly useful for these studies because it is both nearby and highly stable. Its proximity, around 1,000 light-years, means that its pulses are strong and less affected by interstellar medium irregularities than more distant pulsars. Its high rotation rate produces a consistent, easily measurable pulse train, making it ideal for tracking minuscule timing variations. By including Vela in a pulsar timing array alongside other stable pulsars, astronomers can triangulate the effects of gravitational waves, distinguishing real spacetime ripples from noise in the data. The potential implications are profound. Detecting gravitational waves through pulsar timing could allow scientists to observe massive cosmic events that occurred thousands or millions of years ago, long before the light from those events reached Earth. Unlike ground-based detectors such as LIGO or Virgo, which are sensitive to high-frequency waves produced by the final moments of black hole or neutron star mergers, pulsar timing arrays are sensitive to low-frequency gravitational waves. These may be produced by supermassive black hole binaries at the centers of galaxies or by other large-scale cosmic phenomena. Vela's pulses thus act as a slow-motion, galactic-scale interferometer, capable of revealing ripples in spacetime on scales far larger than anything achievable in terrestrial labs. Moreover, the glitches in Vela's rotation may themselves provide additional opportunities for detecting gravitational effects. Sudden changes in rotational speed could interact with passing gravitational waves in subtle ways, producing observable effects in the timing of pulses. While these interactions are still theoretical, they demonstrate the potential richness of using pulsars as tools for both astrophysics and fundamental physics. Observing Vela over decades not only tracks its internal dynamics but also continuously samples the gravitational environment of our galaxy, offering the possibility of detecting signals from some of the most massive and distant objects in the universe. Pulsar-based gravitational wave detection complements other methods and extends our reach across different frequencies and cosmic timescales. While LIGO and Virgo can hear the last few seconds of a neutron star merger in the local universe, a pulsar timing array can effectively listen to centuries-long waves produced by supermassive binaries across billions of light-years. Vela's pulses, as consistent as the ticking of a metronome, become part of a vast cosmic sensor network, allowing humanity to detect space-time ripples that would otherwise remain entirely invisible. The broader significance is that by combining the timing of Vela and other pulsars, scientists can explore phenomena that are not directly observable in light or electromagnetic radiation. Gravitational waves carry information about the distribution of mass and energy in the universe in a fundamentally different way than photons do. By using pulsars as natural probes, astronomers can study the formation and evolution of supermassive black holes, trace the dynamics of galaxy mergers, and test general relativity in conditions that are otherwise inaccessible. In essence, the Vela Pulsar, a star born in a supernova over 11,000 years ago, may help humanity listen to the universe itself, detecting ripples that ripple across galaxies and through time. Its pulses, steady yet occasionally punctuated by glitches, act as markers in spacetime, measuring subtle distortions caused by colossal cosmic events. The very precision that allows Vela to be used as a clock also allows it to serve as a detector of some of the most energetic and cataclysmic phenomena in the universe. Having considered how Vela might help in the future detection of gravitational waves, we can turn to the historical context of its discovery and role in astronomy. The pulsar's identification marked a turning point in our understanding of neutron stars and stellar evolution, transforming what was once theoretical into a tangible, observable phenomenon with far-reaching implications for astrophysics. The discovery of the Vela pulsar, and pulsars in general, marked a revolution in astronomy, fundamentally altering our understanding of neutron stars, stellar evolution, and the life cycles of massive stars. Before pulsars were observed, neutron stars were largely theoretical. Predicted in the 1930s as remnants of supernova explosions, they were considered exotic and almost speculative objects. Dense cores composed primarily of neutrons, the result of a star collapsing under gravity after exhausting its nuclear fuel. No one had directly observed these objects, and many astronomers questioned whether they could exist in nature at all. The discovery of pulsars in the late 1960s, beginning with the first detection by Jocelyn Bell Burnell and Anthony Hewish, provided direct evidence that neutron stars were real, transforming them from theoretical constructs into observable, measurable objects. The Vela Pulsar, in particular, played a pivotal role in this transformation. Its relatively close proximity, just 1,000 light-years from Earth, and its brightness made it one of the first pulsars studied in detail. Observations of Vela confirmed that neutron stars could rotate at astonishing speeds, emit regular beams of radiation, and interact with their surroundings in profound ways. These findings validated decades of theoretical work and opened a new field of study focused on compact objects and their behavior. Before pulsar discoveries, supernovae were understood primarily as spectacular explosions marking the death of massive stars. However, the identification of pulsars like Vela revealed that supernovae leave behind incredibly dense and dynamic remnants, not just diffuse clouds of gas. This insight refined our understanding of stellar evolution, showing that the death of a massive star is not simply an explosion but also the birth of a compact, energetic, and long-lived object. By observing the Vela pulsar and its surrounding supernova remnant, astronomers could link the explosion that occurred roughly 11,000 to 12,000 years ago to the formation of a neutron star, providing a complete narrative of stellar life cycles from birth to explosive death and beyond. The Vela pulsar also helped reveal the diversity of neutron star phenomena. While all neutron stars are incredibly dense, Vela showed that they could exhibit rapid rotation, produce gamma rays, generate pulsar winds, and occasionally glitch in unpredictable ways. This complexity challenged simplistic models of neutron stars as inert stellar corpses and highlighted the need for more sophisticated theories that could account for superfluid interiors, magnetic field dynamics, and particle acceleration in extreme conditions. The pulsar's multi-wavelength emissions, from radio to gamma rays, provided a blueprint for studying other neutron stars across the galaxy, demonstrating that these objects were far more than curiosities. They were active players in galactic ecosystems. The discovery of Vela and other pulsars also had broader implications for high-energy astrophysics and fundamental physics. By offering a natural laboratory for matter at nuclear densities and extreme magnetic fields, pulsars allowed scientists to explore conditions previously only imagined in theory. Vela's predictable pulses and energetic emissions enabled experiments that tested quantum mechanics, relativity, and nuclear physics on scales impossible to replicate in Earth-bound labs. In doing so, it positioned pulsars as key probes for understanding the universe's most extreme environments. In addition, the Vela pulsar illuminated the relationship between supernova remnants and compact objects. The Vela supernova remnant, a sprawling shell of gas and dust surrounding the pulsar, provided visible evidence of the star's explosive origin. By linking the pulsar to its remnant, astronomers could reconstruct the dynamics of supernova explosions, study the distribution of ejected material, and examine how a neutron star's rotational and magnetic energy shapes the surrounding medium over thousands of years. This connection between pulsars and supernova remnants became a cornerstone of modern astrophysics, helping scientists understand not only the fates of individual stars but also the broader evolution of galaxies. The Vela pulsar also contributed to the development of new observational techniques and technologies. Its rapid pulses required precise radio and high-energy instruments capable of resolving millisecond-scale phenomena. The methods developed to observe Vela laid the groundwork for pulsar surveys worldwide, leading to the discovery of hundreds of additional pulsars and enabling projects such as pulsar timing arrays for gravitational wave detection. In this way, Vela not only advanced theoretical understanding but also drove technological progress in astronomical instrumentation and observational methodology. Theoretical constructs into observable, measurable objects. The Vela pulsar, in particular, played a pivotal role in this transformation. Its relatively close proximity, just 1,000 light-years from Earth, and its brightness made it one of the first pulsars studied in detail. Observations of Vela confirmed that neutron stars could rotate at astonishing speeds, emit regular beams of radiation, and interact with their surroundings in profound ways. These findings validated decades of theoretical work and opened a new field of study focused on compact objects and their behavior. Before pulsar discoveries, supernovae were understood primarily as spectacular explosions marking the death of massive stars. However, the identification of pulsars like Vela revealed that supernovae leave behind incredibly dense and dynamic remnants, not just diffuse clouds of gas. This insight refined our understanding of stellar evolution, showing that the death of a massive star is not simply an explosion but also the birth of a compact, energetic, and long-lived object. By observing the Vela Pulsar and its surrounding supernova remnant, astronomers could link the explosion that occurred roughly 11,000 to 12,000 years ago to the formation of a neutron star, providing a complete narrative of stellar life cycles from birth to explosive death and beyond. The Vela Pulsar also helped reveal the diversity of neutron star phenomena. While all neutron stars are incredibly dense, Vela showed that they could exhibit rapid rotation, produce gamma rays, generate pulsar winds, and occasionally glitch in unpredictable ways. This complexity challenged simplistic models of neutron stars as inert stellar corpses and highlighted the need for more sophisticated theories that could account for superfluid interiors, magnetic field dynamics, and particle acceleration in extreme conditions. The pulsar's multi-wavelength emissions, from radio to gamma rays, provided a blueprint for studying other neutron stars across the galaxy, demonstrating that these objects were far more than curiosities. They were active players in galactic ecosystems. The discovery of Vela and other pulsars also had broader implications for high-energy astrophysics and fundamental physics. By offering a natural laboratory for matter at nuclear densities and extreme magnetic fields, pulsars allowed scientists to explore conditions previously only imagined in theory. Vela's predictable pulses and energetic emissions enabled experiments that tested quantum mechanics, relativity, and nuclear physics on scales impossible to replicate in Earth-bound labs. In doing so, it positioned pulsars as key probes for understanding the universe's most extreme environments. In addition, the Vela Pulsar illuminated the relationship between supernova remnants and compact objects. The Vela supernova remnant, a sprawling shell of gas and dust surrounding the pulsar, provided visible evidence of the star's explosive origin. By linking the pulsar to its remnant, astronomers could reconstruct the dynamics of supernova explosions, study the distribution of ejected material, and examine how a neutron star's rotational and magnetic energy shapes the surrounding medium over thousands of years. This connection between pulsars and supernova remnants became a cornerstone of modern astrophysics, helping scientists understand not only the fates of individual stars but also the broader evolution of galaxies. The Vela Pulsar also contributed to the development of new observational techniques and technologies. Its rapid pulses required precise radio and high-energy instruments capable of resolving millisecond-scale phenomena. The methods developed to observe Vela laid the groundwork for pulsar surveys worldwide, leading to the discovery of hundreds of additional pulsars and enabling projects such as pulsar timing arrays for gravitational wave detection. In this way, Vela not only advanced theoretical understanding but also drove technological progress in astronomical instrumentation and observational methodology. Finally, the historical significance of Vela is tied to its role in shaping our view of the cosmos. The pulsar demonstrated that the universe contains objects that are simultaneously tiny in size yet vast in influence. Dense stellar remnants that can emit more energy than entire star clusters, sculpt nebulae over light years, and serve as precise cosmic clocks. Its discovery confirmed that the universe is far more varied and energetic than previously imagined, inspiring generations of astronomers to seek out other compact objects, explore their physics, and unravel the mysteries of stellar death and the exotic remnants left behind. In summary, the Vela Pulsar occupies a central place in the history of astronomy. It provided the first concrete evidence of neutron stars, clarified the connection between supernova explosions and compact remnants, revealed the extraordinary dynamics and energy of pulsars, and opened new frontiers in high-energy astrophysics, relativity, and nuclear physics. Its discovery transformed our understanding of stellar evolution, showing that the death of a star is not an endpoint but a gateway to a new, energetic phase in which a tiny, dense object continues to shape its cosmic environment in profound ways. Having established Vela's historical significance, the next focus is on the cosmic fireworks it left behind, particularly the supernova remnant and the ongoing influence of that explosive event on the surrounding galaxy. The story of the Vela Pulsar would be incomplete without considering the cosmic fireworks that accompanied its birth. Roughly 11,000 to 12,000 years ago, the massive progenitor star of the Vela Pulsar reached the end of its life and exploded in a spectacular supernova, one of the most energetic events in the universe. This explosion released more energy in a single moment than the Sun will emit over its entire 10 billion-year lifetime, scattering elements into space, generating shockwaves, and producing a vast, glowing shell known today as the Vela supernova remnant, Vela Senior. The supernova itself would have been visible to ancient humans on Earth, perhaps even shining during the day for weeks or months, leaving a permanent mark on the galaxy that we can observe today. The Vela supernova remnant is an extraordinarily detailed and complex structure, covering over 8 degrees of the sky, roughly 16 times the diameter of the full moon. This makes it one of the largest supernova remnants visible from Earth, although its diffuse emission requires careful observation to fully appreciate. The remnant consists of an expanding shell of gas and dust, remnants of the star's outer layers, accelerated outward at speeds of thousands of kilometers per second. Over the past 11,000 years, this shell has continued to expand, gradually sweeping up interstellar material and forming intricate filaments and arcs that are visible across radio, optical, X-ray, and gamma-ray wavelengths. Each of these features encodes the history of the explosion and the dynamics of the expanding debris. One of the most striking aspects of the Vela Senior is its multi-wavelength brilliance. In radio wavelengths, astronomers can map the structure of the remnant's magnetic field and detect the synchrotron radiation emitted by electrons accelerated to near-light speeds by the shockwaves of the explosion. X-ray observations reveal hot gas at millions of degrees, tracing the energy deposited by the explosion and the ongoing interaction between the pulsar wind and the surrounding material. Optical observations highlight filaments of ionized gas that glow in characteristic emission lines, showing the distribution of elements such as oxygen, sulfur, and hydrogen. Gamma-ray observations, meanwhile, detect the most energetic particles accelerated by the shockwaves and pulsar wind, providing insight into cosmic ray production in supernova remnants. The Vela Senior is therefore not just visually stunning, it is a multi-messenger laboratory that allows astronomers to study the physics of shockwaves, particle acceleration, and supernova energetics. The Vela supernova remnant also provides a unique spatial relationship between a pulsar and its remnant. Unlike many supernova remnants in which the central neutron star is difficult or impossible to locate, the Vela pulsar sits relatively close to the geometric center of its remnant, allowing astronomers to directly link the pulsar's properties with the explosion that created it. This connection gives a rare opportunity to study the life cycle of massive stars in a single system, from pre-supernova evolution to the explosive death and the subsequent long-term evolution of both the pulsar and the surrounding gas. By examining the remnant structure, scientists can estimate the energy of the explosion, the mass of ejected material, and the initial conditions that led to the formation of the neutron star. The filaments, arcs, and cavities within the Vela Senior also tell a story about the interaction of the supernova with the interstellar medium. As the shockwave expands, it compresses and heats the surrounding gas, creating turbulent flows and instabilities that shape the filamentary structures seen today. Some regions show signs of collisions with denser interstellar clouds, while others are smoother, suggesting less resistance. These variations provide insight into the density and composition of the interstellar medium in our galactic neighborhood, turning the Vela Senior into a cosmic map of its local environment. In addition, the supernova left behind enriched material containing heavy elements such as carbon, oxygen, silicon, and iron, the building blocks for planets, life, and future generations of stars. Supernova remnants like Vela are thus engines of chemical evolution, seeding the galaxy with elements synthesized in the progenitor star and during the explosion itself. Over tens of thousands of years, this material mixes with the interstellar medium, eventually contributing to the formation of new star systems, making Vela not only a remnant of the past but also a contributor to the ongoing cycle of cosmic creation. The Vela Senior is also notable for its detailed observable structure. Unlike more distant or obscured remnants, Vela can be studied in high resolution across multiple wavelengths, allowing scientists to observe shockwave interactions, filament formation, and the impact of the pulsar wind in near real time. Observations have shown that the pulsar wind from Vela energizes portions of the remnant, carving out cavities and producing bright knots of emission, revealing how the pulsar continues to influence the environment thousands of years after its formation. Ultimately, The Vela supernova and its remnant represent a cosmic spectacle of energy, matter, and light, an event of both historical and scientific significance. The explosion was powerful enough to leave behind one of the brightest and most detailed supernova remnants in the sky, providing astronomers with a rich field for studying the life cycle of stars, the physics of supernova explosions, and the long-term interactions between neutron stars and their surroundings. Observing the Vela Senior is not only a window into the past, showing the dramatic death of a massive star, but also a glimpse into the ongoing processes that shape our galaxy and create the ingredients for future cosmic evolution. Having examined the cosmic fireworks left behind by the supernova, the natural question arises: why is the Vela Pulsar still such a mystery after decades of study? Defying complete understanding despite its accessibility and proximity, its enigmatic nature highlights the limits of even our most sophisticated observational and theoretical tools. Despite decades of intense study, the Vela Pulsar remains one of the most enigmatic objects in the sky, a cosmic paradox that continues to challenge our understanding of physics, matter, and the life cycles of stars. On the surface, it seems like a well-understood system, a rapidly spinning neutron star emitting precise pulses of radiation, surrounded by a spectacular nebula, born from a supernova that occurred roughly 11,000 years ago. Yet, despite its proximity, just 1,000 light-years away, and the wealth of data collected across radio, X-ray, and gamma-ray wavelengths, fundamental questions about its interior and behavior remain unanswered, making it an enduring mystery. Perhaps the most puzzling phenomenon associated with Vela is its glitches. These sudden, unpredictable jumps in rotation are not fully understood, despite their critical importance in revealing the star's internal dynamics. Glitches suggest that the pulsar's interior is far from uniform or inert. Many scientists believe that a superfluid core lies beneath the rigid crust, storing angular momentum that is occasionally transferred to the crust, resulting in a sudden spin-up. However, the exact mechanics of this transfer remain elusive. How do superfluid vortices interact with the crust? What triggers their sudden unpinning? Why do glitches vary in size and timing, sometimes occurring after months and other times after years of apparent rotational stability? These questions linger, illustrating how much remains hidden in the hearts of neutron stars. Even more profound mysteries lie in the very composition of the neutron star interior. The densities within Vela exceed that of atomic nuclei, reaching conditions impossible to recreate in laboratories on Earth. Theoretical models suggest a complex arrangement: a solid crust of neutron-rich nuclei, an inner layer of superfluid neutrons and superconducting protons, and possibly even more exotic states of matter, such as hyperons, deconfined quarks, or Bose-Einstein condensates. No one knows for certain what exists at the core. Observations of Vela's pulses, glitches, and energy output provide constraints, but they cannot yet definitively reveal the exact configuration of matter in these extreme conditions. Each pulse carries a clue, but the full picture remains tantalizingly out of reach. The pulsar's magnetic field and magnetosphere add further layers of complexity. Vela's field is billions of times stronger than anything achievable on Earth, and it shapes the motion of charged particles, the beaming of radiation, and the dynamics of the surrounding nebula. While models can describe general features of the magnetic field and its effects, the detailed interactions between magnetic field lines, relativistic particles, and the star's interior remain poorly understood. How does the field evolve over millennia? How does it interact with glitches or with the pulsar wind? These are open questions that defy simple answers. The Vela Pulsar also challenges our understanding of high-energy astrophysics. Its gamma-ray emission is extraordinarily bright and precise, yet the exact mechanisms by which rotational energy is converted into such powerful beams remain incompletely modeled. Similarly, the connection between glitches, magnetic field dynamics, and particle acceleration in the pulsar wind nebula is still the subject of ongoing research. Each new observation refines our models, but also reveals new anomalies, underscoring how even a nearby, well-studied pulsar can elude complete understanding. Part of the mystery stems from the limitations of observation. While Vela is accessible across multiple wavelengths, we still rely on indirect measurements to infer its internal properties. Unlike the surface of a star, which can be imaged and analyzed in detail, the interior of a neutron star is hidden beneath kilometers of ultra-dense material. Every insight into its structure comes from interpreting signals, pulses, glitches, X-ray emission, from the outside, a process that requires theoretical models and assumptions that may not capture the full complexity of the physics involved. This intrinsic opacity ensures that Vela remains partly inscrutable, a cosmic puzzle that challenges even the most advanced physics. Even after decades of study, the pulsar's relationship with the surrounding supernova remnant adds more layers to the mystery. The interaction between the pulsar wind and the Vela supernova remnant is dynamic and ongoing, producing complex shockwaves, filaments, and high-energy emissions. Understanding how the pulsar continues to inject energy into its environment over thousands of years, and predicting how this energy will evolve, remains a major focus of astrophysical research. Each new observation reveals more detail, yet simultaneously raises new questions about energy transfer, particle acceleration, and the long-term evolution of neutron stars. Ultimately, the mystery of Vela highlights the limits of human knowledge when confronted with extreme physics. Despite its proximity and the wealth of data collected, we still cannot fully explain why glitches occur, what the interior is composed of, or how the various physical processes, superfluidity, magnetism, relativistic particle acceleration, interact in concert. Vela reminds us that even the closest and brightest objects in our galaxy can harbor secrets beyond our current scientific reach. It is a cosmic puzzle, tantalizing in its clarity and frustrating in its opacity, serving as both a laboratory for physics and a reminder of how much remains unknown. The pulsar's enduring mysteries are also a driving force for future research, inspiring the development of new telescopes, observatories, and observational techniques aimed at probing its behavior with ever-increasing precision. As technology advances, astronomers hope to unlock more of the secrets hidden within Vela, from the microscopic physics of its interior to the macroscopic effects it imposes on its nebula and surrounding space. Understanding Vela is not just a quest to study a single star. It is a journey to uncover fundamental principles of matter, energy, and the universe itself. Having considered why Vela continues to defy complete understanding, the natural progression is to explore the future of research into this extraordinary object, examining the instruments and observational strategies that will bring new insights into its behavior, structure, and role in the cosmos. The future of studying the Vela pulsar is as exciting as the star itself, with a new generation of telescopes and space observatories poised to reveal its secrets in unprecedented detail. While decades of radio, X-ray, and gamma-ray observations have provided extraordinary insights, the next wave of instruments will allow scientists to probe Vela's interior, magnetic field, and energetic emissions with unparalleled precision, offering the possibility of finally answering questions about glitches, superfluid cores, and particle acceleration mechanisms. On the radio front, large-scale arrays such as the Square Kilometre Array, SKA, and upgrades to existing facilities like the Parkes Observatory in Australia promise to transform pulsar science. These instruments will dramatically increase sensitivity, allowing astronomers to monitor Vela's pulses with microsecond-level precision over long timescales. This is critical for studying not only the pulsar's rotation but also its glitches. By detecting smaller and more frequent glitches than ever before, researchers can refine models of angular momentum transfer within the star and test theories about superfluid vortex dynamics in the interior. High-precision radio timing will also improve pulsar timing arrays, enhancing the search for low-frequency gravitational waves and making Vela a key component in a galactic-scale gravitational observatory. In addition to radio observations, X-ray and gamma-ray space telescopes play a crucial role in studying Vela's energetic output. Missions like NASA's Chandra X-ray Observatory and ESA's XMM Newton have already provided exquisite images of the pulsar wind nebula, revealing arcs, jets, and high-energy filaments. Future X-ray missions, such as Athena, Advanced Telescope for High-Energy Astrophysics, scheduled for launch in the late 2030s, will provide even higher resolution and sensitivity, enabling astronomers to observe changes in the nebula in near real time. These observations will help map the flow of energy from the pulsar into the surrounding nebula, track the evolution of shock fronts, and understand how Vela accelerates particles to relativistic speeds. On the gamma-ray side, missions like NASA's Fermi Gamma-Ray Space Telescope have already identified Vela as one of the brightest sources in the sky, but new and future high-energy observatories will improve the ability to resolve finer details of its emission. For example, the upcoming Cherenkov Telescope Array, CTA, will allow scientists to study Vela's very high-energy gamma rays with unprecedented spatial and temporal resolution. This will reveal how energy is distributed across the pulsar wind nebula and provide insights into particle acceleration mechanisms and magnetic field structure in extreme environments. In parallel, the next generation of multi-messenger astronomy will integrate observations of Vela across the electromagnetic spectrum with gravitational wave studies. By combining radio timing data with other pulsars in a timing array, researchers hope to detect the subtle distortions in spacetime caused by passing gravitational waves. Vela's precise pulses make it an ideal anchor for these measurements. Future improvements in instrumentation and long-term monitoring could allow pulsar timing arrays to detect gravitational waves from supermassive black hole mergers, essentially using Vela as part of a galaxy-spanning observatory that measures cosmic ripples. Space-based observatories designed for neutrino detection and cosmic ray studies may also contribute indirectly to understanding Vela. Its pulsar wind accelerates electrons, positrons, and other particles to extreme energies, potentially generating high-energy cosmic rays detectable near Earth. Instruments such as the IceCube Neutrino Observatory in Antarctica or future space-based cosmic ray detectors could help correlate high-energy particles with the pulsar's activity, providing complementary data on how Vela channels rotational energy into its surroundings. Furthermore, advances in computational astrophysics and simulation will augment observational studies. High-resolution magnetohydrodynamic (MHD) simulations, incorporating relativistic effects and superfluid physics, will allow scientists to model the interior of the pulsar, the formation of glitches, and the interaction of the pulsar wind with the nebula. By comparing these simulations with observations from SKA, Athena, and CTA, astronomers will be able to test theoretical predictions and refine our understanding of the extreme physics at play. Adaptive optics and very long baseline interferometry (VLBI) techniques are also being applied to study the Vela supernova remnant and the pulsar's proper motion through space. Tracking Vela's movement over decades allows researchers to reconstruct the dynamics of the supernova explosion that created it and to model the expansion of the surrounding remnant. These observations will help clarify how the pulsar's energy output shapes its environment over millennia and provides context for the ongoing interactions observed in the pulsar wind nebula. Finally, future missions focused on polarimetry, measuring the polarization of light from Vela, will provide insights into the geometry of its magnetic field and the orientation of its beams. Instruments capable of X-ray or gamma-ray polarimetry, such as the upcoming IXPE, Imaging X-ray Polarimetry Explorer, and potential next-generation missions, will allow scientists to map the magnetic topology and study how it evolves, shedding light on how such fields influence glitches, particle acceleration, and high-energy emission. Together, these ongoing and upcoming technologies promise to transform our understanding of Vela. They will allow astronomers to study the pulsar's internal dynamics, magnetic fields, and energy output in ways previously impossible, offering the potential to answer long-standing questions about glitches, superfluid cores, and relativistic particle acceleration. The combination of high-precision timing, multi-wavelength imaging, and multi-messenger observations positions Vela as a cornerstone object for the next era of astrophysics. As we anticipate these future studies, it is clear that the Vela pulsar is not a relic of the past, but a continuing source of discovery, inspiring new questions about extreme matter, high-energy physics, and the evolution of stars. Its ongoing study will deepen our understanding of the universe while reminding us how much remains to be uncovered. Having explored the promising avenues of future research, the natural conclusion is to reflect on the sense of wonder that Vela evokes, a reminder of the mysteries still hidden in the cosmos and the enduring fascination of a star that spins faster than a helicopter blade, glitches unpredictably, and sends its signals across the galaxy. The Vela pulsar stands as one of the universe's most captivating enigmas, a tiny, dense object born from a supernova thousands of years ago, spinning at astonishing speeds, sending out precise beams of radiation, and yet still defying complete understanding. In every pulse, every glitch, and every high-energy particle it emits, Vela tells a story about the extremes of physics, the life cycles of stars, and the dynamic forces that shape our galaxy. It embodies the paradoxical nature of the cosmos, order and chaos, predictability and mystery, proximity and incomprehensible power, all coexisting in a single stellar remnant. Reflecting on Vela invites not just at its extraordinary physical characteristics but at the broader implications for science and human knowledge. This pulsar, small enough to fit within a city but dense enough to outweigh the sun, challenges our most fundamental theories. It pushes the limits of nuclear physics, superfluid dynamics, relativity, and particle acceleration, all while providing a laboratory in space that is more sophisticated than anything humanity could construct on Earth. Each observation teaches us something profound, yet simultaneously exposes the vast frontier of what we do not know. Its glitches remind us that even objects appearing perfectly regular and stable can harbor hidden, turbulent processes. Its pulses, steady across millennia, show that precision can exist amidst the chaos. Its gamma rays, bright enough to outshine distant galaxies, highlight the universe's capacity to concentrate unimaginable energy in incredibly small volumes. Moreover, the Vela Pulsar is a testament to the interconnectedness of cosmic phenomena. From the supernova that created it to the supernova remnant that continues to expand, to the pulsar wind nebula energized by its emissions, Vela illustrates the ripple effects that a single stellar death can have across light-years of space. Its study informs not only the properties of neutron stars but also the structure of our galaxy, the distribution of cosmic rays, and the dynamics of extreme magnetic fields. In this sense, Vela is both a product of its environment and a shaper of that environment, a key piece in the intricate tapestry of the cosmos. At the same time, Vela symbolizes the limitlessness of discovery. Despite decades of observation using the most advanced instruments, from radio telescopes to gamma-ray observatories, we still cannot answer some of the most basic questions. What exactly lies within its superdense core? Why do glitches occur? How do its magnetic field and superfluid interior interact to produce the complex phenomena we observe? These unanswered questions underscore the reality that even in our own cosmic neighborhood, mysteries abound, challenging us to develop new instruments, new models, and new ways of thinking about the universe. Yet it is precisely this combination of knowledge and mystery that makes Vela so compelling. It reminds us that the universe is not fully mapped, not fully understood, and that each discovery opens the door to deeper questions. It teaches humility, showing that even with advanced technology and centuries of accumulated knowledge, the cosmos retains secrets that are beyond immediate comprehension. And it inspires curiosity, encouraging scientists and the public alike to look upward, to measure, observe, theorize, and wonder. In contemplating Vela, we are reminded of the infinite scale and complexity of the universe. This pulsar, so small in physical size but so vast in influence, is a beacon of both human understanding and cosmic mystery. It stands as an invitation to explore further, to refine our theories, to build ever more sensitive instruments, and to embrace the unknown. Its precise pulses, powerful gamma rays, and unpredictable glitches are not just astrophysical phenomena. They are markers of the boundaries of knowledge and the potential for discovery. Ultimately, the Vela Pulsar embodies the duality that drives science, the known and the unknown, the measurable and the inexplicable. It reminds us that the universe is a vast, intricate puzzle, and that even a single star can illuminate countless mysteries about matter, energy, time, and space. Every observation brings new insights, but also reinforces the sense of awe and wonder that is fundamental to the human pursuit of knowledge. As we continue to study Vela with next-generation telescopes, arrays, and observatories, it will undoubtedly reveal more surprises, deepen our understanding of physics under extreme conditions, and perhaps even provide glimpses of phenomena we have not yet imagined. But for now, it stands as a cosmic lighthouse, a pulsar whose relentless rotation, brilliant emissions, and persistent enigmas remind us that much of the universe remains hidden, waiting for discovery. Vela Pulsar is more than a star. It is a symbol of the infinite possibilities that lie ahead in our exploration of the cosmos, and a constant call to marvel at the mysteries still beyond our grasp. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.